Okay. So we're gonna continue to talk about MIPS, and right now we're gonna, hopefully today we'll have time to just do a very simple operation, very simple instruction. But before that, we do need to introduce a few terms. There's this term called registers. And registers, you can think of registers as variables, but they're in the hardware. So unlike any programming language, any high-level programming language, assembly uses registers, and those registers are actually in the hardware. So, for example, so PC, the program counter is a register. So program counter is actually a register. And this register, again, you can think of it as a variable, except that it's in the hardware. Now, in assembly, you have access to those registers. So you can write code that actually gives you access to those, again, storage spaces in the hardware. In C, you cannot do that. In C, you can create variables, but those variables, you don't know kind of which register we're talking about. Of course, ultimately, those values will end up in the hardware, but we don't know where exactly they end up. But when you write an assembly, you're actually talking about the registers that are in the CPU directly. So these are what registers are. They're not variables. You can think of them as kind of storage spaces like variables, but they're in the hardware. And when you do an operation such as addition or subtraction, you use registers. So registers are the operands to operations. So the operands are you can think of it as the arguments for operations. So when you add two numbers, the two numbers are the operands. Now, of course, because they're in the hardware, because registers are in the hardware, you have a limited number of those registers. You can't just say, one day you want to wake up and say, I'm going to create a new register. You can't do that because registers are in the hardware. When you bought your computer, you bought the CPU, and some number of registers were already built in the CPU. This is very different than variables. So we have a limited number of those, and because they're built in the hardware, and the operations can be performed on registers. I think this kind of implies that. So when you try to, add, multiply, subtract, you can actually use the registers and the content of those registers to do the operations. And because registers are on the CPU, they're on chip, that's what they're called, meaning they're on the CPU chip, they're extremely fast. So they're very fast. You don't have to go to the RAM to bring them. If they're in the CPU, if the value is already in the register, then you can just use it to add or multiply or, do any operation you want. Going to the RAM is actually very slow compared to kind of just using the registers on the CPU. All right. Since registers are built in the CPU, there's a predetermined number of them. That should hopefully make sense, because these are, again, they're hardwired. They're built in the hardware. Because of that, there's only a limited predetermined number of them. In MIPS, the MIPS that we're going to study, we're going to have 32 general purpose registers. Now you can see that we're using 32 a lot. 32 is the number of bits in the bus. 32 is the number of bits, in the registers. And we also have 32 registers. So 32 is used a lot. And of course, that's not a coincidence. That's because we like 32. 32 is a power of 2. And 32 is a good number, not too high, not too low. That works out really well with the MIPS CPU that we're going to be studying. So in the CPU, we're going to have 32 general purpose registers that we can use when we write MIPS code. Now, one thing that I mentioned before is that program counter is another register. This is not a general purpose register, but it's another register. And it's not only that we have 32 general purpose registers, so the size of each of those registers is going to be 32 bits. So to summarize, let me summarize that here really quickly. Kind of in the MIPS that we'll be studying, which is called MIPS 32, we'll have 32 general purpose registers. This one not including the PC, the program counter. That's the first one item. The second item, the size of each register, including the PC, the program counter, is going to be 32 bits. So we have 32 general purpose registers. The size of each one of those is 32 bits. And of course, the other things that I mentioned, right? So, the data bus is 32 wires, the address bus is 32 wires. The size of each instruction is 32 bits, which is 4 bytes. So 32 is pretty, it's a number that again is used quite often here. All right. So in MIPS, we have 32 general purpose registers. We talked about that. And those registers are numbered between 0 and 31. They're numbered from 0 to 31. Each register can be referred to by a number, one of those numbers between 0 and 31, or a name. All of those have names, by the way. All of those 32 registers have names. You don't need to memorize all of them, but I'm going to ask you to memorize some of them at the beginning. So you can refer to them by doing $, then followed by the number. So essentially, when you do this in MIPS, you're talking about register number 1. When you do this in MIPS, you talk about register number 2, which is really register 1. And this is register 2, which is really the third register. Hopefully that makes sense. Now, those registers from 16 to 23, they have the names S0 to S7. Now, why they have those names and what do they mean? We're going to talk about that later. Those registers from 8 to 15, they have names T0 to T7. And that's something that I want you actually to memorize. And it's actually not very hard to memorize. Let me show you a trick here to memorize this. Let me start with a new slide here. So can you give me tell me how 16 looks like in binary? How does 16 look like in binary? I'm going to actually have a table. I think a table is going to be better. So I'm going to have 16. I'm going to start actually with 8. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to probably stop here. Okay. So I asked about 16. Grace told me it looks like this. Let me first make it all text. We go to cell So 16 is going to be 1 0 0 0 0. That's good. How about 8? Okay, that's good. Let's do 0 1 0 0 0. Let's do 5 bits for all of them. I'm going to do 9 0 1 0 0 1. I'm going to do 10 0 1 0 1 0, 11 0 1 0 1 1, 12 0 1 1 0 0, 13 0 1 1 0 1, 14 0 1 1 1 0, 15 0 1 1 1 1, and 17 1 0 0 0 1, 18 1 0 0 1 0. Okay, and I'm not going to do the rest, but this is just enough. So those 8 to 15, those are the T registers. These are from T0 to T7. So let me change the color of this one. And I want you to kind of memorize that. So whenever you see 10, I'd like you to say, oh, this is T2. Now, how can you do that? Of course, you can memorize all of that, but there's an easy way to do it. You look at the two most significant bits. The two most significant bits are going to tell you whether the register is a T register or an S register. If the two most significant bits are 0, 1, like this, then it tells you it's a T register. Is that good, guys? Let me pause here and see if you have any questions, if that makes sense. We look at the two most significant bits out of those 5 bits. If it's a 0, 1, then we can say it's a T register. Now, we need to determine the number of the T register. You know how we do that? By looking at the 3 least significant bits. Can I change the color of this? Yeah, I don't know if you can tell, but this is more of a red. So again, we look at the two most significant bits. We see 0, 1, so we say this has to be a T. And the reason why I do a $sign, because it's a register name or register number. We always use the $sign before the register name or the register number. So we say it's a T. Now, what is the value of those 3 bits? 0, so it's a T0. Very simple. How about this one? Well, we look at the two most significant bits. There's 0, 1. That means it's a T. What's the value of those 3 bits? So it's a T1. How about this one? Can you help me with this one? What is this one? You see where my mouse is? Help me with this one. What is this one? This one is T what? T4, exactly. Why? Because this is a T, 0, 1 is a T, and the value of this one is 4, so that's going to be T4. So it's really not that difficult. And this is T5, and this is T6, and this is T7. Now for the S's, I only have 3 examples, but it's actually a very similar procedure. We look at the two most significant bits, and in this case, there would have to be 1, 0 for you to say that it's an S. So you look at the two most significant bits, you see 1, 0, you say it's an S, and then you look at the 3 least significant bits, and that's going to tell you the number of the S register. So in this case, it'll be S0, and in this case, it'll be S1, and in this case, it'll be S2. Of course, here we have T2, T3. Do you have any questions about this? All right, it seems that this makes sense. And this is really what this slide is saying. It's saying that we have from 0 to 31, you can use the numbers, but also you can use the names. And I showed you a way to go from binary to names, at least for the T registers and for the S registers, not for all the registers, because we have 32. We have more registers that you haven't seen here. Okay. So a machine instruction is going to look like this sequence of zeros and ones. Let me actually maximize here. So what you're seeing here is an example of a machine instruction. It's actually similar to what we've seen at the beginning, of MIPS in the previous video. And what happens is the CPU, when the CPU gets this pattern, it's gonna decode it. That's the term that we use, decode. So decoding means we're gonna look at specific parts of that instruction, and we're gonna deduce kind of knowledge from those parts. So those 6 bits, now of course you don't have to memorize that, but this is just an example. Next week, you're going to be very good at that kind of stuff. Next week, you're going to be very good at decoding those. You're going to become like an assembler, because that's what the assembler does. The assembler is going to, excuse me, that's not what the assembler does. That's what the CPU does. And you're going to become kind of like a CPU, where you look at the machine code and you execute the instruction, or at least you tell me, what that instruction means. So those 6 bits, this is just an example. I'm going to just, go over it. We don't have to memorize any of that. But those 6 bits, the most significant 6 bits and the least significant 6 bits, is going to tell us something about the operation. So in this case, it's going to be addition. So we're going to look at the 6 most significant bits, the 6 least significant bits, and we're going to deduce the instruction. That's going to be, in this case, addition. And then we're going to look at 5 bits here, and that's going to give us the first operand. And then we're going to look at the 5 bits after that. That's going to give us the second operand. Again, that's just an example. You don't have to memorize that. And then this one's going to give us the register that we're going to put the result in. And these 5 bits are things that I'm not mentioning here, but you can ignore them for now. Okay, now I have a question for you. What is the name of this register, which is really the first operand? Look at it. What is the name of this register? Based on what we learned 2 minutes ago. S1, that's great. Grace is saying S1, perfect. Oh, actually, no, I take it back. It's not S1. And let me go back here. The S registers are going to have 1 0 in the most significant bit. What do we have here in the in the 2 most significant bits? Exactly. We have T1 in this case. This is a T register, so this is a T1. So the first operand is T1. How about the second operand? What is that? T3. That's very good. How about this destination or the result register? What is this one? S0. Perfect. So before I go to the next slide, let me show you something here, because I think I think it's worth spending another 2 minutes here. Essentially, in your CPU, we have registers. Now the CPU is big because I need to put some stuff in it. So we have registers, and I'm going to say, this is T0. Then I'm going to have T1. And you know what I'm going to do? I'm going to copy, then I'm going to say paste, which will keep the font. And then I'm going to do paste, paste, paste. I actually don't want to list all of them. I'll just do a T3 here. And I'll do S0. Let's do S1. I'm not listing all of them, right? There's 32 of those. And they have names that we haven't talked about. I'm just going to kind of list a sample of those. Now, when we say that the first operand is T1 and the second operand is T3, and the result needs to be stored in S0, what that essentially means is, actually, let me do a text here. What that means is take T1, add to it whatever is in T3, and put the result in S0. Now, again, this is kind of important for us to understand. So I told you that you can think of those registers as variables. They're storage locations. However, they're in the CPU, they're in the hardware. And when the CPU looks at this instruction and when it decodes it, when it says, oh, there's 6 bits here and 6 bits here, that means it's an addition. Okay, what do I want to add? Well, let me look at those 5 bits. Those 5 bits are giving me T1. Okay, so I need to get the content of T1. How big is T1? Can you tell me how many bits is in T1? I told you this before. How many bits is in T1? Exactly. So Kate is saying 32. Perfect. We have 32 bits here. That's absolutely correct. So I'm going to get the content. I'm going to get those 32 zeros and ones. And then I'm going to add them to the second operand, which is in this case T3. So I'm going to get, the content of T3, which is here, and I'm going to add it to the content of T1, and I'm going to put the result in S0. So I'm going to add, again, the content of this one. Let me change the color of it. I'm going to get the content of this one, and I'm going to add it to the content of this one. And I'm going to put the result in S0, which is this one. Does that make sense? Give me thumbs up or thumbs down if that makes sense. Okay, it's perfect. So that's really what this instruction means. And again, we're going to get better at decoding those instructions. So in other words, it means S0 is equal to T1 plus T3. That's really what it means. That is, so this binary, this machine code means, get the value of T1, get the value of T3, add them up, put them in S0. And that's what the CPU is going to do. Now, let me show you how this is written in assembly. So this is machine code. I'm going to show you how you write that in assembly, and then we can stop and continue tomorrow. In assembly, it looks like this. You actually have to say add. So this notation is not allowed. You cannot say something is equal to this plus this. You can't do that. What you would do is the following. I'm going to actually do it here. You would say add. Then we would put the destination, which is S0. Then you would say the first operand, and then you would say the second operand, like that. Let me put it here. So that's how you would do it in assembly. So when you want to write code in assembly, which we're going to do tomorrow. Tomorrow, I'm going to get, at the beginning of tomorrow's class, I'm going to install a piece of software with you that will allow us to write code in assembly, in MIPS assembly. So it looks like this. This is a command. And what this means is get me the content of S2, get me the content of S1, get me the content of S2, and put the result in S0. So if we know that the value of B, which is a variable in C, from this basic instruction in C, if we know that the value of B is stored in S1, and if we know that the value of C is stored in S2, and if we know that we want to use S0 for A, then this line in C is really the same thing as this line in MIPS. Because this line in C is going to add B to C and put it in A. And this line in MIPS is going to add S1 to S2 and put it in S0. And again, if we know that B1 is going to be stored here, C is going to be stored here, and we'd like to use S0 for A, then this MIPS code is the same thing as this C code. It's kind of they do the same thing. That's what I mean by the same. Okay, so Katie's asking a very good question. What makes those 6 bits plus those 6 bits addition? Well, it's because of their value. So your answer or your guess is correct. When those 6 bits, when the most significant 6 bits are all zeros, and when the least significant bits are all zeros, then followed by a 1, then that's really the shape. That's a combination that means addition, and it'll mean addition every single time. So this is the shape, and there's in the CPU itself, there's some sort of dictionary. So the CPU is gonna, it's like a dictionary where it looks at the shape and it says, oh, this is addition. So if you want to do subtraction, you have to change the shape. If you want to do multiplication, you have to change the shape. You can't have the same shape. And again, you don't have to memorize that kind of stuff. This is just an example. These are called fields. So when you have an instruction, those instructions are divided into fields, and each field means something. And there's actually multiple ways to divide an instruction into fields. So this is something we'll have to talk about at some point. But for now, this is just an example. If you understand it, and it seems that you do, that's perfect. All right, so I think this is a really good place to stop. We started with just one example in addition, kind of adding in MIPS. And tomorrow we're going to probably review this part and do more examples. So we'll do addition, subtraction, and maybe another instruction. Do you have any last minute questions before we end it? All right, perfect. We can end it here. Thanks for again attending those Zoom sessions, and I will talk to you tomorrow.